I know you guys are on lesson like 6 or something now, but I just want to go through and kind of touch base on each one just to kind of make sure you guys know where you're at. So the lesson number 4, I gave you your first CPR quizzes. There were 2 on there, number 1 and number 2. Number 1 came from the old exam, which I think is useful just to see. And then number 2 is the pilot from last year, which is what's going to be more similar to what you guys are getting. So the first CPR quiz that I was looking at, they gave you an example of going down a sand dune and thinking about the energy changes from there. So being mindful that, you're starting with gravitational energy and then it's going to get converted into kinetic energy. Something to keep in mind when we're looking at these bits of information is that energy is going to be lost, often in the form of heat, which is why the next chapter you guys are looking at right now is on heat transfer, because we're trying to think what happens to the energy if it's not going into motion. There's also a big tie between motion and heat, because particles moving faster is what's causing heat to occur. So that's what the first quiz is looking at, and just doing kind of that math and that conversion. You're basically using some of these calculations up here. So this one over here is going to be your gravitational potential energy. This one is your kinetic energy that you're looking at. And you can rearrange those equations to figure out what the kinetic energy is going to be for each one. And basically what you should be seeing is that there's energy loss because not all of the energy is getting converted. You okay with that? Do you want me to do any of the calculations just to see how they work? Yep. Okay, let me grab it. Oh, I grabbed my pens. Ha ha ha. All right. Are we okay with the gravitational potential energy question? That one's just the mass times gravity times height. I feel like that one's straightforward enough. Yeah. So you just plug in the numbers there. The kinetic energy one's a little bit more complicated because you have the v squared. And so you have a little bit more when it comes to how you're thinking about that. So in that second question here, they're saying her speed at the bottom was 12 meters per second. Calculate the kinetic energy that she has when she's at the bottom of the hill. So let's get to the document camera. I'm recording it so that way you guys can always refer to it later. All right, so kinetic energy, KE, is 1/2 mass times velocity squared. So if I know the other variables, then I'm able to plug it in. One of the things that I was taught when I was learning physics that I find really helpful is listing out my knowns and then listing out my unknowns so I know how to rearrange the equation. Wow. So my knowns in this case would be, we know her mass and we know her velocity. So velocity, we know it's 12 meters per second squared. And, 12 meters per second. Not squared, we're not talking about acceleration. And then we know her mass is 55 kgs with the same word. So when I'm doing this and my unknown, is that KE. So if I was to put in the equation that I need, it's going to be this one up here. The challenge you guys are going to face with this assessment is that you are going to need to know from that list of equations which ones you need for which assessment. Sorry, which question I should say. Lady, I'm trying to get some notes. All right. So when I go to my equation, I'm then plugging in those values and using that equation. Sorry, just getting this to focus. So KE is equal to 1/2 my mass, which is 55, times v squared, which is 12. So I do 12 times 12 when I see v squared. And that's how you set up that one. I don't have my calculator with me, unfortunately. We'll go grab it if you guys are curious. But that's what you're looking at. So we want 0.5, calculator, 0.5 times 55 times 12 times 12 again. And so I get 3,906 joules. So that's how you're doing those calculations there. Now, something to keep in mind is that, like I said, was the previous exam version. It's slightly different now. In this case, it's a little bit more theory. So in this case, we're talking about someone waiting for the bus, and they're talking about the football and throwing the football vertically upwards. It has the mass of the football. It also has the height that you reach, and then you also have the speed in which it hits the ground. Lady, trying to give notes. All right, so they want you to write the equation. So that's just talking about the energy transformation. This one here is where it gets a little bit trickier than we've seen before. I'm finding all my typos. So I want you to calculate the size of the average force of friction between the ball and the air. Begin by showing that on the way down, on the highest point, you have 0.537 joules of mechanical energy is being changed to other forms. So for this second question, what we are thinking about is how much energy we have at the beginning and then what is it getting translated to. Just grabbing a marker. So when we think about our gravitational potential energy, because once again, we're talking about that, we have gravitational energy is equal to the mass times gravity times height. So the mass is that 0.5 kgs. Sorry, 0.150 kgs. Gravity is always 10. We simplify it. It's actually 9.8, but we use that number instead. And then h, which is our height, is 3.4. So we do that calculation, and then we should get an energy value. So we have 0.15 times 10 times 3.4. And so I get that my gravitational potential energy is going to be 5.1 joules of energy at that point. Now, what we can see in this question is that it's not that value. We can see that it's actually on its way down from its highest point. That is the amount of mechanical energy being changed, but then where is it going? So that's what we need to think about. So we need to be mindful that there's friction occurring because the ball's falling down and interacting with the air. So basically, we need to figure out what the friction force is. So we need to figure out how much work is getting done and then the distance that is happening. I believe, let me just double check to make sure I'm going the right way. Yep, that's all right. Cool, kinetic energy, just double checking what that is. Okay, cool. So, all right, the other thing we're going to need to know is what the kinetic energy is. So we're trying to verify that that's the energy that's lost to heat. So redoing that doing another version of that equation, just like we were looking at. The gravitational energy, sorry, not gravitational, the kinetic energy is 1/2 the mass times velocity squared. Again, we're just plugging in our numbers times 0.150 times our velocity, which is 7.8 squared. So that's times it by twice. So a lot of calculations when you guys are doing this one. Mistake. There we go. So this one is showing that the kinetic energy is 4.563. And if we do a subtraction between these two, we can actually see how much you're getting lost in that heat experiment. Not the heat experiment, the difference from R2. So in theory, it should be the same, but obviously it's not because we are losing energy to heat. So this is the difference that we're seeing is 0.537 joules. So that confirms the number that they have given us. Oh. See? Same number that they've gotten. All right, so I verify that that's the right answer. Now I got to think about, okay, what is the force of friction that's occurring? So we're thinking about this work equation over here. Oh, I'm surprised I put this in here because it's now work. All right, so that's good. Then it starts talking about the next lesson. All right, so work is equal to the force divided by the distance traveled. The force is what's going to be our friction that's occurring. So if I rearrange this equation, I can then figure out the F value, which is what I'm trying to do. So we know that we have, just trying to find another color. So we now want to use the work equation. Work is equal to the force times the distance traveled. We do know what the work is because we're using that number there. And then we do know the distance because the ball has dropped and the ball has moved 3.4 meters. So if I rearrange this equation, I have F equals W divided by D. Are we okay with how I just rearranged that? So all I did was divide each side by D to get my F by itself. So I can take that number and divide it by 3.4. And now I know that the force of friction is 0.15. Let's round up to 8 newtons. That's how we get that answer. So if we look at the marking schedule for this guy over here, see how all this working is over there. Mechanical energy is lost to the environment, so that's going to be lost as heat, which is what you guys are moving on to now. This is the answer. And this is how the marking schedule works. So first off, either showing that you know the gravitational potential energy is 5.1 or you know the kinetic energy, that is an achieved level because you need to do that working first off. That's your first step in these calculations. Second step is then you can either talk about the size of the friction between, like where is that friction coming from? It's the ball in the air, but you calculate that with a minor error. So that's why it's really important to show your work. Because if you make a mistake, we can then backtrack and go, oh, you just forgot to square it here. That's one minor error. I can still give you a merit point for it. If you don't show any of your working and you get the wrong answer, we can't give you any points. This one here, you calculated both those correctly and you show that the difference is that. That was also considered for a merit point. So either you got the calculation most of the way there, you just made a mistake, or you got this one right. And then lastly, for the excellence, you show the size of friction between the two with the calculations. So the nice thing about this assessment is that it's very math focused. So if you can show the math of what you're doing, then you can usually get your points. Are we okay with that? All right, cool. That's not too bad. I'm just going to stop it here. I want to see if there's one